In this unit, we're going to study complex numbers, which is right here. If you notice that complex numbers is beyond the real number system we've been constrained from, right? All the studies so far remained in the real number system, and this is the first time we're heading out to that system. We're marching into the complex number system. So again, the bigger picture here is still we're studying how to solve quadratic equations, but in certain cases, complex numbers is going to come up. So let's look at this example. How can you use square roots to solve this problem? Obviously, we recognize that 16 is a perfect square. So if I want to square root the left-hand side, I can excuse me, I can do that. I have to do that on the right-hand side as well, except that recall from middle school that when you square root a number, there is a principal root and there is a secondary root. So you have to add the plus and minus. And now if I simplify both sides, I would have x equals positive 4 or x equals negative 4. Either number would satisfy the condition that x squared equals 16. Now, in the previous unit, I also demonstrated how to do this by difference of squares. You can just do x plus 4 times x minus 4, excuse me. So now, with this approach, you get to the same solution, x equals 4 or x equals minus 4. Now, let's look at this introduction of complex numbers. The imaginary unit I is the principal square root of negative 1. So in other words, if I do principal square root of negative 1 equals I, I'll probably write it on this side. And now if I square both sides, I would end up with I squared equals negative 1. Okay? So this I represents an imaginary number. There can be a coefficient, which we call it bi, where b is a non-zero real number. So b has to be a real number. So I can have 2i, 3i, and so on and so forth. Now, complex number can be written in the form of a plus bi. So now I have a real number component, and then I have an imaginary number component to it. And so if I have a plus bi, where a and b both are real numbers, and I is the square root of negative 1. That's what we call complex numbers. So let's see how we use this or how we simplify this going forward. Now let's look at how we simplify this. We literally treat the I, the imaginary unit, as a variable. So it becomes nothing more than an algebraic manipulation. So here I have, I'm asked to find the sum of these two complex numbers. It's a plus in between, so 4 minus 11 is minus 4. Negative 7i plus 9i would give me positive 2i. That's it. So that's my final answer right there. Multiplication is no different. We follow the same algebraic rules. Negative 2.5i times parentheses 8 minus 9i. So we just distribute it all together. Negative 2.5 times 8 should give me negative 20i. And over here, be careful, double negative makes a positive. That should give me 22.5. I times I is I squared. Now we apply our new knowledge that this becomes negative 20i, and I squared is negative 1, so it converts this into, and if we want to write it properly, it's the real numbers first, imaginary unit next. That's the final answer to this problem. complex conjugate is really handy. It often helps us to take us out of the complex numbers world and return us back to the real numbers world. So it simplifies our math lives quite a bit. They're complex numbers with equivalent real parts and opposite imaginary part, and the product is a real number. And as illustrated here, so this pair, they're exactly the same, except that the operation in the middle is the opposite. One is plus, one is subtract. If you multiply them together, you end up with sum of squares. So here is the trick. In exams and tests, if I give you sum of squares, you should be able to use this approach and find the two imaginary roots. Simplify quotient with complex numbers. I highlighted the study tip here. It says multiplying the denominator by its complex conjugate will result in a new denominator that's a real number. So what this is saying is that when you have a fraction and you see the imaginary piece, imaginary unit in the denominator, very often we go for the conjugate so that that will give us a real number and helps us simplify it. So it's asking, how do I write the quotient 10 over 2 minus I into the form of complex number a plus bi? So I keep the numerator the same, and then the denominator I'm going to multiply 2 plus I. And if I do that in the denominator, I shall do the same upstairs in the numerator, right? And now if I simplify this, I should have 20 plus 10i on top. At the bottom, I should have 4 minus I squared. And we all know minus I squared is really plus 1, isn't it? So I should have 20 plus 10i. I'm sorry, excuse me. Made a mistake there. That's a 1. I squared is negative 1. Now I go back to divided by 5. And if I further simplify this, is 4 plus 2i is my final answer there. So again, when you see conjugate in the denominator, when you see imaginary units in the denominator, use conjugates often get you into the real number world. In this example, we're asked to factor the sum of squares. We know we can factor the difference of squares easily, so the first thing we need to do is to rewrite the sum of squares into a difference of square by adding a double negative in there. Okay? Now the question is, how can I convert that that negative y squared, make that into a perfect square? Okay, here's where the magic happens between the real number world and the complex number world. Now, if I just pay attention to this negative y squared, just the inside part, and I'm going to rewrite it into negative 1 times y squared. We also know I can rewrite negative 1 into I squared times y squared. So if I put the y in the front, because the coefficients usually is in the front, what I can do is I can simplify this into yi squared. Now if I put it into my original equation, I have x squared plus y squared equals, I rewrote this, x squared minus negative y squared becomes yi squared. So now the difference of square is very easy to solve. It's x plus yi times x minus yi. And that's my two factors of the sum of squares. Okay, So again, the trick is that in the real number world, you can only factor the difference of squares. In the complex number world, you finally can factor the sum of squares. But in order to do that, you have to play around with the imaginary I so that it works in your favor to convert the sum of square into a difference of square first. Here's one last example. Again, it's sum of squares, so I'm going to rewrite that into a difference of squares, except that I'm going to rewrite that into 2i squared. 2i squared would give me positive 4, right? So after that, it's now a difference of squares, so, oops, sorry, I missed the I there. So my final solution are x equals positive 2i or x equals negative 2i. And here it is. So finally, here's a summary of complex numbers. And the important key information is I is root 1, root of negative 1, and therefore I squared equals negative 1. And for complex numbers, we have a real number plus an imaginary number, so a plus bi. The operations are very algebraic. Just treat the I as a variable, follows all the PEMDA rules. And then finally, when you take care of divisions, when you take care of the denominator in particular, we introduce the concept of conjugate, which uses the difference of squares to move you from complex world into the real number world. Okay, not hard at all, but very handy, very successful. This is probably the only time that you will see complex numbers in the high school curriculum, unless your teachers do some review, but it's really all here. It doesn't go much beyond that until you go to college and truly study math.